Well, hello, it's Cliff here again, riding the ThreadExpress. Let's start by rolling a short introduction of what ThreadExpress 2.2 can do. And we've got our skewed scallops. It's a little thumb grip. I'll show it to you in its application in a minute. So all of these tests are coming out really well. Machining hexagon nuts with threads. Can machine bolts all in the one setting, the thread and the hexagon. And from the previous video, tests such as machining a very small, slender 3mm screw that's less than 1/8 of an inch with thread milling, much lighter machining loads than you get with screw cutting. Larger parts that are made out of 4140, a much bigger part here. So particular job illustrates the advantages of thread milling for this type of application, where you need a very accurate pitch over a long length, where you need to get right down to the shoulder so the cutter can swing round really close there, and you don't want to have an undercut for screw cutting because that will weaken it and reduce the length of the thread. And where you want to machine it in a high tensile steel, this is high tensile steel. And you can see the cutter there is just shy of the base. Set the unit to the correct pitch thread, juggle the cutter in to the existing thread until you're just touching on the gullet of the thread like that, and then just wind it on and extend the thread as far as you want to go. And tungsten carbide fly cutter, for example, will very easily cut high tensile steel bolt. But you try doing that with a die, even a high-speed steel die. It's a massive task. They're expensive, and you'll chip the teeth of the die after a couple of bolts and very quickly destroy your threading die. Okay, well, let's first quickly talk about the response to the last video. Thanks very much for your comments. It had about 4,100 views, which is quite a lot for my channel. You probably know my channel is not all about presentation. I throw the videos together pretty basically and quickly, but I want there to be good content in this channel. Okay, so 4,100 views is pretty good. That attracted about 46 comments, starting comments. There were follow-up comments to a lot of those. From those 46 comments, let's just break down what the demand and interest looks like. Well, about 25 of them, of people, are just curious. They want to know how it works. In this video, I will reveal some more, and probably in the next video it will be fully revealed. But there were only about 10 people that wanted plans and wanted to build it. And I'm reading between the lines. I'd say there's probably 5 of those are possibles, and the other 5 probably would go ahead and build them. So out of 4,100 views, we would end up with about 5 of these being built around the world. Nobody has committed to wanting to purchase one, to wanting me to build them one. Okay, so I want to try and understand why the demand so far has been quite low.
Well, maybe we could start by looking at the negative comments to try and understand what it is. So one of the negative comments that was repeated several times is that it's an outdated technology. I mean, people don't know what the technology even is. So are we threatened by something unknown? It's not a known thread generating mechanism as far as I'm aware. I've been doing a deep dive into the history of mechanisms and looking at hundreds of different historical examples of pitch generating mechanisms and other similar mechanisms, and I've yet to find one the same. So are we threatened by the fact that, well, you know, we don't need it? We don't need to try and understand something new. We have existing technology. We have CNC. A lot of people are saying, well, you have CNC, you don't need anything else. Okay, well, not all shops have CNC. Probably most small shops don't have CNC around the world. Are they going to buy a CNC vertical machining center just to do thread milling? A lot won't. And also, with a CNC, you can't cut accurate thread forms. I know that's going to get a lot of arguments stirred up, but you don't have the adjustment of the helix angle by interpolating a cutter around the inside or the outside of a thread. And I'll go into that, I have gone into that in previous videos, and I'll go into it again in this video. It's not accurate, not highly accurate. It does a good enough job for producing nuts and bolts and fasteners, but be aware it's not an accurate process. With an attachment like this, you can tip it over at the helix angle and you have the ability to produce accurate thread forms. So that's one criticism. We already have existing CNC. Why do we need to learn anything new? Now, the other criticism is that, well, why wouldn't you just use an NC, numerical controlled pitch generating mechanism? Why do you want to have a mechanical one? Well, you don't know how simple this mechanical pitch generating mechanism is in the first place, but let's say it was very complicated and expensive. It may be cheaper to use a numerical control pitch generating mechanism. That is, you would have a ball screw and nut, you would have stepper motor, you'd have a pulse generator, and you'd have some little mini computer controller to link it all up. Well, okay, they're all off-the-shelf components and they can be picked up pretty cheap, and a lot of people are capable of putting that together. But don't forget, that's not the sum total of what this is. You still have to have a headstock, you still have to have a spindle and a chuck, and you still have to have bearings, you still have to have slideways, you still have to have a housing. What we're comparing about is the mechanical pitch generating mechanism cheaper or more expensive than the NC pitch generating mechanism?
Okay, so I've taken the covers off this prototype, and at the end of the video I will reveal it a lot more closely, but please stay with me for a few more minutes and listen to my explanation of the situation.
So I'll go on and show you now some of the features of this thread cutting attachment. I'm not desperate to manufacture this or to get this out there if there's no demand for it. I'm trying to ascertain, well, what is the demand for this machine? Is there resistance because people are philosophically opposed to trying to learn something new? There's a percentage of viewers who did comment encouraging positive comments and were fascinated, would have loved to know how it worked, and some would even love to build one. But out of 4,100 views, that's a tiny percentage. I'm really curious as to why it's not in more demand, and if I can be convinced that there is very little demand for this, then I don't want to take it any further, because that's a big job. You know, the procedure for developing a product is time consuming. I have built 3 prototypes, type 1, type 2, 2.1 and 2.2. Well, if you count the first one, that's 4 different prototypes. And the next stage is to build a production model and refine it down to a version 3.0, where all the little details are sorted out, because prototypes are just hacked around versions and they're not designed for manufacturing finished production model. So a 3.0 production model would need to be redesigned. There would be new CAD files, and I'd need to really make a sample of it. We're talking a lot of time to get that up and running. Then I'd need to produce technical drawings, plans, printable PDFs and so on. We're talking many hours, and if there's only a demand for a small number of enthusiasts who want to build it, it just can't be justified. I've just got a lot of other more important things to do than that, unfortunately. Maybe one day when I'm older and retired I could tackle it, but at the moment it just can't be justified. So I'm challenging you. Are you sure that you don't see any demand for this product around the world? Are you really sure?
So that was one roughing cut depth of about 0.9 of a millimeter with a single toothed fly cutter running at 2,500 RPM, and one finishing cut taking it depth down to about 0.94 millimeters. The thread depth for 1.5 millimeter pitch 10 millimeter metric thread. And I've got a nut here that's threaded the full length, so you can see the accuracy of the engagement. The pitch is not out at all, because that part was cut on ThreadExpress in a few minutes. Now I was just thinking, just for interest, let's compare cutting it by a more traditional method using high-speed steel split dies. And I've got an M10 die set up in this floating die holder in the lathe, and I've set up the same steel, put in an undercut with a parting tool, and ran the lathe and cut the thread with the die. And you can see it's sort of taken a while to get started on the thread, and then it's cut the thread quite well as far as the undercut. But it doesn't cut an accurate thread using a die. Now of course you can cut an accurate thread on a lathe by screw cutting with a single point threading tool, but you would need a center in the end to support the tool, to support the work. You'd need an undercut to run into it. You'd need to set it all up very carefully, take multiple cuts and screw cut the thread. That's a much bigger job. It's equally quick to use a die though, and let's just have a look at the quality of the thread cut with a die compared with the thread milling machine attachment. Okay, well let's look at that thread we've cut with the die. It looks okay, a little bit rough, but it looks okay, and a nut will run on it okay. So you think everything's fine, and it's good enough for making nuts and bolts, but if you want to do precision work, it's really not good enough. If you have a look at this thread more closely with, for example, a longer thread gauge, you can see that the thread is out. I've discussed this in the previous videos. I don't know if I can show it there very clearly, but see, I have to rock the gauge to keep it in the thread. It's actually progressively getting out of pitch, and that's because the thread die is a relatively short length and it's resisting cutting it. It's only being pushed by the few threads behind it, and it's slowly losing pitch. If I put on it a nut that has a decent length of engagement, for example this one, I get about halfway down and it starts to get tight. So you're not getting a precision thread using a die, and even although a nut will go on, as you tighten it, it's not tightening over the full length of the thread. It's not an ideal situation. You compare that with screw cutting, or in this case thread milling, and you get a much more accurate thread. You see there it's matching the thread gauge well, and this nut, which is the full length, will go on the full length. So it is a much more precision process than using a die. You can screw cut in a lathe, but that's a highly skilled job, and you need to use multiple passes. You need to support it with a center, you need an undercut for tool clearance, and it's not the sort of thing you can do quickly. And I know I've had in the comments some people say, well, just rough it out in the lathe almost to depth and then run your die over it, and that's a quicker process. Well, yeah, that is a bit quicker, but you still have to go through the procedure of putting in a center, putting in an undercut, taking multiple cuts, then putting on a die and cutting it with a die. And it will follow the thread then, because you've already established the pitch, and it won't drag and go out of pitch. But how many people go to all that trouble? Okay, I've been getting a few questions about whether or not you need to set the helix angle when you're thread milling. So here I've made a bit of a mock-up of a 3D version of a large thread. So you can see there I've got two of them in white, just in some bellows covers. And if it was a convex shape, it would be an external thread. If it was a concave shape, it would be an internal thread. This is just flat, but it demonstrates the principle. And here we have a mock-up of a cutter. See if I can hold that a bit better. Okay, so it's circular in its trajectory. It doesn't matter whether the cutter is a fly cutter or a multi-tooth cutter. It describes a circular path, and that shows you the approximate form of it there. So if this is the center line of the spindle, the cutter is at right angles to the center line of the spindle if you are vertical thread milling in a 3-axis CNC machining center and so on. So the cutter trajectory is set like that. Now if you set it at the helix angle, then it drops down into the valley of the thread. The cutter goes into the valley of the thread and comes out the valley of the thread parallel to the valley of the thread. But if you don't set the helix angle, you can see, I don't know how well this is coming up in the image, you can see there, maybe I need to move the light, you can see the cutter, it doesn't really show, does it? But I guess you can imagine that cutter going down parallel into the valley of the thread with a helix angle set cuts the correct form. But if it's not got a helix angle set, it starts to cut up the sides of the valley of the thread into the flank of the thread form and gives an error. Now this varies depending on the pitch of the thread and the diameter of the thread and the diameter of the cutter. There are three variables, but in some cases the problem is very little, and in other cases the problem is much bigger. And for high precision work, for example thread grinding, when you have a grinding wheel like that, you mustn't have any profile errors in the thread, because you high precision thread grinding and thread grinding machines all have helix angle adjustment facility, and it's really important for precision work. So if you're vertical thread milling, be aware of the fact that you could be machining errors in your profile of your threads. I know that some of you continue to question me about this. There's a lot of information online from the high-end tooling manufacturers such as Sandvik Coromant or Iskar. Here's one from Sandvik Coromant showing the single tip threading tools in a lathe situation, showing it tipped on an angle of the helix angle. Cutting edge clearance between the sides of the insert and thread flank is essential to ensure even tool wear and consistent high quality threads. The thread should therefore be tilted to gain maximum symmetrical clearance from the flanks, flank clearance angle, and get the correct thread profile. The tilt angle of the insert should be the same as the helix angle of the thread. That is that angle there, and that's the tilt angle. Let's have a look on another article from Iskar, showing the little
insert, incorrect, set level, correct, set to the helix angle. Let's scroll down to page 16. Here, a thread milling anvil is designed with annular cutting edges without helix angles. Thread milling is performed when the axis of the cutter and the axis of thread direction are parallel to each other. An incompatibility in the direction of the cutting edges with the threading direction causes geometrical distortions during thread machining. This is the problem with thread machining in a 3-axis vertical CNC machine, is that you do get errors. The geometrical distortion of the thread profile increases as the thread pitch increases and the end mill diameter increases, which can be explained by an increase in the contact angle of the end mill with the workpiece. Okay, the moment we've all been waiting for, let's reveal a little bit more of the design of this invention. So here we have the hand wheel. We'll do a bit of a slow walk around, shall we? Here's the side with the hand wheel, and that turns the spindle. You can see there it's basically a bevel gear with a 4:1 ratio. Now, whether there's a mechanical pitch generating mechanism or an NC pitch generating mechanism, you still need that mechanical reduction internally so that you can wind the spindle at about the right speed for thread cutting. On the end we have a precision plunger that locates in holes in an index plate to set it and lock it at different positions for index machining. So we'll come around to the end. You can see there the carriage plates, the scales that are shown in the last video for setting threads per inch and millimeters pitch. That's the single adjustment there to the pitch. And we're going to come around here to the chuck with its resettable dial for different degrees. I think I mentioned that in the last video also. There's a very simple pitch generating mechanism inside the headstock, and you people are having trouble guessing it because I don't think it's ever been thought of before. I may be wrong about this, but the reason why I don't think it's been thought of and why thousands of people have thought of it but dismissed it in their head, as I did, is that it appears to defy logic. The first time I thought of it was in my sleep. My subconscious mind thought of it. And when I woke up, I thought, no, that wouldn't work. You're crazy. Go back to sleep. And then my subconscious mind thought of it again. And I woke up again. That wouldn't work. Go back to sleep. And probably thousands of people have thought of this simple mechanism and thought, well, that wouldn't work. I'm not even going to embarrass myself by talking about it with someone else, let alone making a prototype. And so I just think it's skipped being discovered until now. And inside there is a very simple mechanism. Historically, people have come close to discovering it. There were French watch-making machine builders back in the 1600s, 1700s that came close to it, but I cannot find a mechanism anywhere in the world that is the same. I've had a couple of comments by people that say, why would you want a thread cutting attachment when you can just screw cut in a lathe? You know, a center lathe, single point screw cutting, that's what they're for. Yes, of course, single point screw cutting in a lathe is a brilliant process if you want to cut a large thread in stainless steel or high tensile steel, because you have a big powerful headstock. You've got the rigidity, you can use a tailstock to support the other end, and you can take multiple cuts. It takes a lot of torque to cut a large thread. But what if you want to cut a slender thread, a small thread, a medium-sized thread up against the shoulder, where you don't want to have an undercut? The cutting forces of thread milling are much lighter. Thread milling has been established for many years as a better process for small to medium threads where you're coming up against the shoulder. It is quicker and the machining forces are much lighter. It takes a light scalloping cut, whereas screw cutting takes many, many passes and the load on the tool and on the work is much higher. You get much more tool and work deflection
with screw cutting compared with thread milling. So there are many areas where thread milling is a better process, and there are many areas where screw cutting in a lathe is a better process. It's horses for courses. It depends on the particular job you are doing.
So I'm challenging you to have a careful think about this and let me know in the comments, do you think it's got a future or do you think it hasn't? Try and come up with a good, logical, rational reason why not. Because I think we are biased, philosophically we are biased as human beings to steer away from anything that is new and requires time and effort to try and understand. But I'd really appreciate it if you could think about it and comment. Stay with your negative point of view if you still feel negative. But if you can see a positive future for it, please tell me. And then I can ascertain whether I should continue to work on this project. Alrighty, thanks very much. Thanks for watching. Please like, subscribe it if you haven't already. And that will help this whole thing to become more clear.